Good morning, everyone. Thanks, Alex, for the kind introduction and reminding me that I'm getting old. Thanks, Sabina, for inviting me to this conference, nice conference. And CrackPass was my first conference as a PhD student, so it's a great honor to be back and present my, let's say, the recent results that we obtained to you. So today I'll talk about fretting fatigue and additive manufacturing. I will also talk about the effect of microstructure and heterogeneity on the crack cost. So somehow to link these things to this conference. I would like to thank my PhD students, Grzegorz, my postdoc Sanjay, and also the people from Mechanical Engineering Department who helped us to 3D print these samples. So additive manufacturing, we have heard it a lot here and there. I think these years it's become a hot topic even by a lot of industries being used. I'll quickly talk about the process. So it starts with the model, a 3D model like this, and then the metal powder, and then the powder would be spread on the bed. Let's say I'm talking about laser powder bed fusion technique here. And the laser melts the powder, and then we can make the shape, and then that process is continued till we have the final part. So we start with a kind of CAD model, and then we end up with a complex shape. And it's been very interesting for industry, at least on their website. For example, here you see that they claim that it would result in 50% reduction of the lead time, 75% less development, and can work at high temperatures because of the internal features that we have, and can go up to 13,000 RPM. So it's beneficial for them. This is the application that you see. For example, one of the applications, the blade is being, let's say, connected in a way to the disc. But the question is, okay, what is the structural integrity of this part? There has been a lot of work on fatigue and fracture behavior of AM part. But when it comes to this kind of applications, there are a lot of contacts here. And then we are talking about some problems like fretting fatigue, which is a tribal mechanical problem. So in this presentation, I will try to answer this question: what is the impact of fretting fatigue on AM made part? So to do that, first I will introduce the fretting fatigue and just briefly talk about, okay, what is the failure mechanism? Then I will talk about the experimental setup and numerical models that we developed, and then some results and discussion, and hopefully in the conclusion, I can provide some information about, okay, what is that effect and some future work. So fretting fatigue. I'll start with the application that I showed. There are two possibilities. We could have ductile, let's say, blade disc attachment, or a kind of PL3 blade disc attachment. In both of them, at contact interface, because of the two, let's say, forces that we acting on the blade, attention and also the vibration, we get a complex loading conditions at the contact interface. So there is a kind of normal load and tangential load, which causes high multi-axial non-proportional loading conditions at that location. It becomes more complex because the contact status is different at the contact interface. So then we have middle of the contact sticking, and at the edge of the contact, there are some small sliding. So that would turn into crack initiation at the contact interface. It would propagate in the mixed mode because of the influence of the contact, and then it causes the final fracture of the part. So it's a mixture of tribal mechanical fracture. So the objective of this work that I'm presenting is, okay, what is the impact of fretting fatigue on a part like this, which is made of AM material? So the idea came from a literature review that I did, I think, around 2018. And since now there is only one published data, some Italian colleagues, they got this type of specimen, they call it blade root, and that was made of intermetallic alloys using electron beam melting technique, and they did 3 tests at a very high temperature. And the mechanism was exactly the same, so crack initiation at contact propagates till the failure of the blade. In their conclusion, they mentioned something interesting. So they said the fatigue cracks propagate even in the gross sliding condition. And the crack propagation is very fast for this AM made material. To understand these two, let's say, conclusion points, we have to understand this graph. What is this graph? This graph is a relationship between the wear process or tribological behavior and the mechanical response of the material. So the blue curve that you see is showing the fatigue life, and the red curve that you see here showing the tribological response of the material. And we see that as there is a minimum lifetime. So it means that if you are at this relative displacement between the blade and the disc, the lifetime is minimal. So if you increase the displacement, we go to gross sliding. So it means that the cracks normally for normal material would be removed because of the wear. So there is less chance of fatigue problem, so it becomes more wear problem. If we decrease that, we go to the sticking area, so we have less wear problem, but also very high fatigue lifetime. So the critical point is in the partial sleep, then you have sticking and stealing. So that triggered something in my mind, but at the same time, I was very surprised that they did not talk at all about internal processes, because AM is somehow linked with the internal defect. So the year after, in 2019, I published the work. So I got some materials like aluminum, which is made of electron melting, and then it's very common for this kind of materials that you get cluster of defect because of the process. So I simulated the threading fatigue contact problem. So this is the threading pad pushed against the specimen. The specimen is shackled, and we have a tangential load to create a tangential stress distribution. And then I randomly distributed some properties inside the material. Interestingly, I found that, okay, 60% of course, it's a worst case scenario, and that's for aluminum. 60% of the crack initiation sites are not at contact interface. So there is a kind of competition between high stress, multi-axial stress at contact interface, and also the stress at the processing levels. And then luckily in 2020, I got 2 projects, and then I got some money to work on my own, let's say, experimental setup. So this is a build print. This is a very big build print. It's 30 by 30 centimeter size, and these are the experimental setups or test specimens that we made. These are the 2 experimental setups that I will introduce. So what you see here is the machine. Actually, the technique was later called bed fusion, and these are the printing parameters. Just to give you an idea about the printing parameters, we collaborated in industry. There were at least 2 PhD students that optimized these printing parameters. So then we were somehow sure that we get a good quality material. If you see, the density is 99.66%. We did some heat treatment, so at 850 in argon for 2 hours, and followed by cooling in the furnace. This is the kind of practice for industry. And then we, let's say, manufactured samples using using wire EDF. What you see here, the first one is called the dovetail blade setup. The second one is called the bridge type setup. The bridge type setup is mainly based on the ASTM standard for fretting fatigue, but it's mainly a kind of recommendation. It's not really a standard way of testing. It's just introducing different way of testing fretting fatigue. For the specimens, the roughness parameter is very important. So it was 0.9 micrometer after the post-manufacturing, and the RC is also very important. It was around 6.38 micrometer. So I'll briefly talk about this setup, but I do not present the results of this setup because my PhD student will present that today at 2:30. But I will compare some results with the bridge type setup. So it's more like a component test. The other one is more like a kind of lava scale test. So here, what you see, this is a fixture. It's fixed at one side, and the let's say the fatigue stress is applied at the other side. 2 contact pads are pushed against the specimen. We cycle that, so the contact stress is also cyclic because it's the reaction force between the specimen and the pads. And the crack initiates at least we hope the crack initiates at the contact interface and propagates the failure of the specimen. Here you see the let's say the shape of the specimen and the 2 types of pads that we use: incomplete contact, which we can call cylindrical contact, and also complete contact, which we can call flat contact. One of the important factors here is this angle, because that can change the stress distribution not only at contact interface, but also at other locations like these neck areas, which are the transition areas. In literature, we find 35 to 55 degrees for that. And then it went for the more challenging one, which gives us a, let's say, kind of similar or at least minimum difference in the stress distribution at contact and also at the neck area, just to see what would be that effect on the AM material. For the bridge type contact, so this is the specimen, the pad is pushed against the specimen, so this is a kind of bridge type pad. The dimension that you see here gives us a kind of relative displacement to generate the slip at contact. In this case, the ring is used to apply a kind of uniform normal load, and one side of the specimen is cycle. So in this case, the contact load is fixed. In this case, it was 2 kilonewtons. So I will mainly talk about the results of this, let's say, standard test. So I will talk about the materials that we use. So this is the, just to make sure that there was nothing wrong with the material. So it was typical alpha beta, let's say, Ti 6.4, and these are the two vertical and let's say horizontal samples, the grains that you see here. We did not observe anything abnormal about this 3D printed material. We did some tensile tests. Here you see the comparison between the let's say the AM1 and the raw material. The elongation was higher. Let's say the yield stress and ultimate stress, and also the modulus of plasticity were lower compared to the raw material. But it was typical to the previous print jobs, and also the one that industry uses. So we were not surprised with these differences. Another important factor was, okay, for this type of setup, we have to make sure that we maintain the contact load during the test. Otherwise, the impact will be huge on the crack initiation and response of the material. So we try to monitor let's say, the contact load by putting some strain gauges here during the test. So in the initial part, you see that it's called the initial stage, 1,000 to 2,000 cycles. There is a kind of a drop in the load, but stays constant till the end of the test. And the initial value was 2 kilonewton, but if you see the contact load, I think it was acceptable. So there was not that much drop in the contact load. Here are some initial results. What you see here is a force against number of cycles for this type of, let's say, setup. And interestingly, we saw that 30% of the 10 tests, 30% of the tests failed outside of the contact. So that was an interesting observation. But we also see some kind of scatter in the crack location. So 3 tests failed at the transition area, the rest, they fail at contact interface. So to understand what's happening here with this load that we're applying, we did some finite element simulation. With the finite element simulation, we could understand the contact status. Is it partial slip or gross sliding? So for the first 3 loads, you see this is the frictional shear stress distribution. And for the model, we used a kind of 2D model here with a coefficient of friction of 0.55, which we measured using digital image correlation. But my student will present that this afternoon. So I will not talk about that. But this is how we set up the model. So the contact load is applied and then the axial stress applied at the other side. But this frictional shear stress distribution gives us a kind of idea about the contact situation. So here you see that from here to here, this is sticking, and at the sides, it's sliding. So if we get the kind of full curve here, it means that it's sliding. So using this kind of information, we know that, okay, 3 first loads are partial slips, and the 3 last ones are, let's say, gross sliding. So then we know that, okay, these tests were done under partial slip condition, and these tests under gross sliding. So what we can see, one of these tests that done at gross sliding failed outside of the contact. For partial slip, it was more competition between the high respiration at the contact and outside of the contact. To compare the data that we obtained, we tried to get some raw material data from literature, and here you see a comparison, and also the plane fatigue data. So here is the, let's say, machine specimen which are additively manufactured using the same material. Here is the electropolished samples of AM, and these ones, the diamond, are the, let's say, as-built condition. And these blue circles here are the fretting critique tests done by our colleagues in, let's say, the United States. So what we realized in the first point that, okay, if we get only the cross-sectional stress, so this is only the cross-sectional stress and it took into account different R ratios. We see that, here the AM material and the rod material, they are close to each other, but of course the number of cycles or the behavior is more like as-built condition. To understand that better, we can plot this graph which shows us the roughness values. So here, for the machine one, we have 4.1 micrometer. For the electropolished one, 2.7 micrometer. For the as-built condition, we have 8.6, which is very close to what happens in fretting fatigue. So if you have a fretting fatigue problem, and if the crack initiates at contact, so it's very similar to the as-built fatigue behavior of the material, if you're additively manufacturing. But of course, this is a cross-sectional stress. We wanted to know what happens at contact because the stress at contact gives us more information. So with the finite element model, we simulated both for rod material from literature and also for, let's say, AM material. And then we realized that okay, with this maximum stress that we can get at the contact, we are closer to each other. Of course, the coefficient of friction is an important parameter here. And what they reported in the literature was a kind of range of coefficient of friction that they observed during the test. But we believe that according to data that they provided, these two materials are more or less the same. But here, we are talking only about stresses. But as I said, slip amplitude plays an important role. So what happens if we plot the slip amplitudes for different tests that we did? Then we get this kind of scatter plot. So then we see that there is no direct link, but we can see that, okay, the AM material is performing, let's say, less compared to the as-built condition. And then we found some parameters that we can combine this slip amplitude and the stress distributions at contact interface, and it's called the effective slip. So it's already published by some colleagues, and we add that together. So we define this kind of damage sensitivity parameter and then also the slip amplitude together, and they take into account the yield stress of the material in this equation. And then they see, okay, they are close to each other, but still we see that the effect of R ratio is considerable for the rod material, but the AM one and the rod material, which they were done at the same stress ratio, they are performing more or less the same. Just to give you an idea about what happened, the other test setup, we also similarly experienced some of the points for the dovetail joint fade outside of the contact. So for this test setup, we could do also tests on the rod material ourselves. So we could have some kind of reference data here. So even for the rod material, because of the angle that I told you, it's very critical. We saw that at some high stress levels, which we have full sliding condition, the samples fade outside of the contact. But for AM material, these two force level and stress levels, we see that 1 out of 4 specimens fade out of the contact interface, so in the transition area, actually. And then we plotted the same values, the effective slips for all the tests, and also got some data from literature with different angles, from 40 to 35 to 45. And we see that, again, because of different mechanical properties like plastic modulus, the AM material, the slip amplitude is higher, or the effective slip amplitude is higher for AM material compared to the rod, but overall, they are overlapping with the data from literature. So, I will continue from now on to show some, let's say, fractography and also tribological properties of the material that we investigated. So here you see the fretted area. If you look at the edge of the fretted area, we see some fretting damage. So these are typical fretting damage, which you can see also for rod material. Here is the let's say EDM surface, and here is the edge of crack. And then we see also some, let's say, in the slip zone, some local damages because of the fretting behavior. If we look at the, let's say, close to the edge of the crack, we see some wear particles as well, or the wear scars, and also some debris particles, wear debris particles, which are again typical for fretting fatigue problem. If you see the fracture surface, it can give us a kind of better understanding what's happening in the test. So here I just take a couple of examples. I'll talk only about one of the samples which failed due to fretting fatigue, and then I will cover all three of them which failed outside of the contact. So what you see here, the green ones are basically the crack initiation locations for fretting fatigue problems, and these three are the ones that failed outside of the contact in the transition area here. And then these are the location of the cracks. So let's start with sample number 2, which is this one. So here we see this is a fretting fatigue failure, let's say fracture surface. We see multiple cracks initiating actually at the contact interface, and then we see this kind of ratchet marks, which shows that this crack propagated and they overlapped each other, and they formed a big crack which propagated till end of the let's say failure of the samples. We see also the cracks happening at the other side of the contact. They are centered. There is no edge effect. That shows that the test was done correctly. And also we see some competition between the cracks forming at this side and the crack propagating at the other side. If we just zoom in, we see that at some points there are some unmelted powders actually in the fracture surface, which is typical for AM material. So let's talk about the ones that fail outside of the contact. The first one, we realized that at the, let's say, 5 kilonewton, sample number 3, we found out okay, there are some porosities or lack of defects which are close to the surface. But the stresses are, normally if there is no lack of fusion or defect, the stresses are at least 200-300 megapascal lower than what happens at the contact. But when you have such a, let's say, internal defect, it acts as a kind of stress riser. The crack propagates in both ways, close to the surface and also in that way. So we also found some kind of inclusions, which could be gas or pore inclusions. For the next one, we also saw the same behavior. So we have multiple locations of crack initiations. Again, we have a cluster of defects forming actually at the close to the contact. And let's see here, you have different porosities, different sizes of porosities. And just to give you an idea about why this is happening, basically this is the as-built surface, and then we use wire medium to cut the surface. So these are basically internal defects which become not surface defects, but near surface defects. And that is very high stress riser. Here you see a lack of fusion, which one gas was, let's say, powder or melted powder was trapped inside. So these kind of upward shape increases the stress distribution and decreases the number of cycles. We saw the same for the last let's say examples. Again, the cracks start at the let's say subsurface porosities or defects, lack of fusion, and propagates to the surface. So all three tests, the crack started subsurface defects. So that was a kind of interesting finding. So even if you have high stress concentration at contact interface, but these kind of subsurface defects could play an important role. It got even worse for, I mean, I'm showing only one sample for dovetail joint because it was a bigger sample, so it was more challenging to avoid this kind of thing. So this is a kind of subsurface defect. It's a very big defect with a cluster of unmelted powder trapped inside that defect, and then the crack is in the neck area propagated instead of the contact. So that's one of the two failed samples outside of the contact area. So the second part is, I think I have some time, 10 minutes. I'll talk about the numerical work. So we did also some numerical work to simulate what's happening actually. So for the crack initiation, we started to use damage mechanics approach. For damage mechanics approach, there are different ways. We use the Chebosh model. Basically, I'm not going to go through the details here, but the damage mechanics approach considers that the one needs to stress and also the stress strategy are responsible to initiate fatigue damage. And then we have some material parameters. The first two can be let's say, calibrated using the basic plane fatigue data, and we recalibrated that for let's say, crack length equal to 28 micrometers, which we found using the theory of distance for this material, according to the data that we had. And the V1 and V2 are mainly the effect of stress ratio. And the A is basically the damage accumulation factor, which we can we calibrate all the parameters using the data that we have. And for crack propagation, we use extended finite element modeling approach. So we inserted the crack here at the location of maximum, let's say, stress, which the crack is supposed to initiate. And then I think the methodology we have published 2 years since 2020, the last 4 years, because the stresses are quite non-proportional and multi-axial here. The crack propagation is governed by non-proportional stress distribution. So maximum tangential stress criteria or these kind of methodologies which are good for proportional loading does not give us the crack propagation path correctly. So if we use that one, so the crack propagates the other way. So what we did, we just get the, let's say, at the half of the critical distance ahead of the crack lip, we get the stress distribution like the stability parameter and multi-axial criteria, and then we get the maximum value which shows the critical plane. Basically, we find the critical plane at the head of crack tip, and then we propagate the crack. So what you see here, they are the experimental data which we got from the 3D scan surface of all the fracture specimens, and this dashed line is the numerical simulation that we do. So we can more or less predict how the crack initiates and propagates in this material, and then we can use a kind of Paris law equation to predict the number of cycles that it takes to propagate the crack from a crack size of 28 micrometer to the final failure of the sample. If we put all things together, you see here, these are the, let's say, experimental, these are the predictions, and the green points are the experimental data, and it overlaps quite nicely here. Of course, this is not something new. There are a lot of things in the literature that you can find that we can predict like that. But the idea of this model is, okay, what can be done next? And that's integrating these defects, integrating some, let's say, heterogeneity of the material. So I'll quickly go through a couple of slides which talks about the, let's say, microstructural heterogeneity. In last year, we published a paper. We found some interesting papers in the literature which they use this kind of stainless steel grain, and then we tried to simulate the grain orientations, actually the grain size and distribution using Voronoi tessellation in Abacus, and then we see the effect of this kind of non-homogeneous distribution of the grain. Here you see that this is the inhomogeneous or non-homogeneous model, so this is a homogeneous model, and then we see the effect of different grain properties here. So that was for steel, so we could propagate the crack as you can see here, so the crack propagated through the grains, and we could predict the crack path at different stress loads, but we saw some minor variation at higher stress levels. And here are the crack, let's say, shapes through the grain. But it was much more complex for AM material. Why? Because in AM you get this kind of microstructure. So what we did, we found some nice ABSD graphs from this absd.com. So they somehow reconstructed this beta shape of the grains inside the Ti material, which is additively manufactured. And we got this data, we post-processed data, we included in the finite element model that we had for AM material. In this time, we went one step further. We tried to simulate the orientation of the grains. So how we did that, we found some test data from literature which they use, let's say, sound wave velocities using this kind of polygon samples, and then we could get orthotropic material behavior for this material, and then we integrated that in the finite element model to see what will be the effect of that kind of anisotropy on the lifetime of this AM material subjected to fretting fatigue. I'm not going to talk about the initiation. I will focus on the propagation, but before that, here you see the stress distribution inside of the grains alongside the contact interface. Here you see how the stress distribution or the the material orientation can change the stress distribution inside the material compared to the homogeneous model. And here, finally, we could simulate randomly some crack propagation models and see how does these cracks interact with the different grain orientations. Here you see the range of, let's say, simulations that we did and the craft passes, and the dashboard is the homogeneous model. So what you see here is, for example, for two stress grains, we see that the crack is going through some grains, but what we can confirm is the fact that the grain orientation governs the stress distribution and direction of the crack. For example, this is a nice one. So all three at the same stress level, three different orientations. So you see here, the orientations are in line. The crack is almost going through that perfectly. Here, you see that the grains are following the orientation. And here you see the orientation is different. And then you see this kind of strange behavior, which governs the crack going from this grain to this grain and coming back to this grain. So I would stop here with the conclusions. From the experimental test campaign that we realized that for fretting fatigue, surface and subsurface defects are very important, but surface defects are mainly due to fretting fatigue, but subsurface defects could be due to the manufacturing process. The fractography shows that these subsurface defects are playing a very important role, and there's a competition between the surface and subsurface defects, and numerical simulation confirms that we can reproduce this kind of phenomenon that we see like microstructure and homogeneity as a future work. We are going to integrate the shape of these internal processes inside the model that we have to see what would be the outcome of the prediction. Yeah, that's it for myself.